All right. This course generally, especially for those of you real interested in mechanical engineering or civil engineering, this leads directly into a course called Structures. This course actually goes by several names. In fact, enough names that I'm not even sure necessarily what we call it in the catalog. But it goes by several names, one of which is Mechanics of Materials. We're going to look at the physical properties of a material and its response to load. So it's also called strength of materials. It's also called things like deformation of elastic solids. If you think about it, that's exactly what we want structural materials to do. We want them to be able to flex under loads, and when those loads are released, they return back to their original condition, ready to take the next load that comes in. Nothing more than what you do when you come into class, and the building, whether you know it or not, actually flexes under the load of us being in here when we weren't in here half an hour ago. And when we leave, the building will return to its original unloaded state. Actually, it's preloaded because the structural members of this building all are holding everything above them, which includes floor, walls, and ceiling, as well as a lot of general mechanical stuff up there. So this course goes by a lot of names, but it does come directly off of the statics we did last fall. Everything we did there is going to lead directly into what we're going to need to do here. One of the very first things we're going to have to determine is what the external loads are. And then from those external loads, we're going to do exactly what we did partway through statics, where we determine the internal loads in the material. That's the static response of the material itself, such that there is internal shear, internal moments. We're going to also add some other types of loads to this, and it's those loads, the material responding to the external loads, that is reflected in the deflection or the deformation of the structural materials that we're going to look at in this class. So that's the basic idea of what we've got going there. These two, the statics and the strength of materials, are so closely related to each other. A lot of schools put these together as a single 4-hour class, where we have them separate as 2 3-hour classes. But they're that closely linked. Our number one tools then, of course, will be that the forces on all our objects will sum to 0, and of course the moments will sum to 0. And that's all forces taken into account in any way, whether they're internal or external to the structural piece itself. It's still going to have to be a static situation for everything that we do. So let's warm up with a real quick little statics problem, and then we'll make the next step as we look into the response of the material and start to get a touch on how things actually deform under these loads. To start with, we won't look at the actual deformation. A couple days away from that, but we will very quickly get to that. So imagine a very simply structured object of some kind where we have two simply pinned straight members holding some kind of load there. Nothing more than we did in statics. In fact, we were doing this kind of thing pretty much in the first week of statics. We went a little bit farther with it as we went along, but pretty much we weren't doing a whole bunch more than things like this in the very first weeks of statics. So it's just a little bit of warm-up, but it also allows us to make the next step as we take a very different viewpoint of this structure than we did in statics last term. Let's say we've got a 30 kilonewton load there, and first thing we need to know is what are the external forces on each of these members. That's going to then allow us to look at the members themselves and see how they're going to respond to those loads. What we did in statics was we used those external loads to figure out what the internal loading was, the response of the material to those external loads. Now we're going to look at the actual physical response of these members react to these loads. We realize, I hope, that this is a 3, 4, 5 triangle, and that means that all of the ratios of all of the forces in this are also of that same ratio. So we can figure out then, based on a force balance at point B here, because that will then give us the forces in the two members, since both the members meet right there, that we can very quickly determine what the external forces are, and then we can make our next step to the new subject matter we've got at hand. So that's 30 kilonewtons there. Obviously, then, let's see, let's label these something. We'll call that FAB and FBC. They also must have the same ratios as that 3, 4, 5 triangle. Let me ask you why. Why must the forces be in the same ratio of 3, 4, 5 that the geometry itself is?
It has to do with the fact that they're in the same directions.
Why are they in the same directions?
Two force
They're
members.
two force members. Both of these, the two structural members, AB and BC, are both two force members. Therefore, we know immediately that the forces lie in the same direction as the members themselves, more specifically in the line connecting the two pins at either end. It doesn't matter what the member does in between, the forces are directed through those two pins. So then we can figure out then what the forces are without having to do too much quick calculation, because we've got the same ratio in the forces that we have in the geometry itself. That's nothing more than anything we would have done in statics. What we're going to do now is take a look at the internal forces that are caused by those loads. So if we bring this little piece over here, blow it up there so that we can see it, we have this, in that case, the 50 kilonewton load is acting throughout this entire piece, and in fact it's spread over that entire cross-sectional area. We'll only draw it for the most part as a single point load, but that's just for a matter of expediency on our part. But there is a bit of a distribution of that force over that area. That should make some sense to you, because in general, a thicker piece of material can hold a greater load than can a much smaller piece of material. Area most certainly does have something to do with it. That's not great news to you. You've got that kind of experience anyway. If you're building a deck, a woodshed or something, you don't want to do it with toothpicks. It's not going to hold. You may want to do it with toothpicks, but you're not going to. There's just not enough material there to support the kind of load you're seeing. And this has to do with this cross-sectional area A. Very quick word about that force distribution over that area. It's not uniform. If we look at it at different places through the piece, it tends to have sort of a distribution that's like that, where most of the force is directed through the center of the piece, tends to drop towards the edges. We're going to treat it even more simply, for the most part, as uniformly distributed, but not even that. We're going to treat it, we're just going to say we have this force acting on that cross-sectional area, and we're not going to worry very much about the precise distribution of the force itself. In more advanced studies of this material, yeah, you're going to have to. But for what we're doing here, and our start on this, we don't need to worry about too much more than just that there's some force in some area as we're concerned with it. So those two quantities, the internal force in a structural member and its cross-sectional area, are right now the two most important things that we have to concern ourselves with. Now, as we look at the material and its response to this, and we're finally now bringing into account more than just the length of the member, which we looked at a lot in statics last term. We're now looking at more of what the cross-sectional area is. It should follow fairly with good sense that the ratio of F over A would have some import to it. Makes sense, I think, as the force goes up, things get worse for the material. As the area goes down, things get worse for the material. So the ratio of the two makes some good sense because it's their movement in opposite directions. As one goes up and the other goes down, both of those contribute to a less advantageous situation for the material itself. And what we're worried about happening in this class is things going to the point where the structure itself fails. Whether the material actually breaks catastrophically, or maybe it just deflects enough that the structure no longer works like it should. It's quite possible that the load could go so low, even though none of the members break, that the structure doesn't do what it's supposed to do in the way it's supposed to do it. So this ratio is very important to us through this class, and we call it the stress, and give it the symbol sigma, great lowercase sigma. And it's the force in a member divided by the cross-sectional area that is supporting that force. More specifically, this is known as the normal stress. Remember the meaning of the word normal to us? Perpendicular. Because this is the situation where the force we're concerned with is perpendicular to the area we're concerned with. And that's indeed the case that we have here, where the force is perpendicular to the area. What that should mean to you is that we can take other areas. They don't have to be normal to the axial direction of the member itself. We're going to look at areas that are taken more on an angle and see what the forces are there. We're going to find out that's very important, because when some of these things fail, they fail not at a direction perpendicular to their own axis, but at an angle off that axis. And you've seen some of this kind of thing before. When pieces fail, they don't fail in a nice cut across the piece. They fail at some angle across the piece itself. So you've seen this kind of thing before. The units, sort of. Two things. One is, you remember our long tradition in the physical sciences of naming sets of units off dead white male German physicists. So this is known as a Pascal. 1 Newton spread over an area of 1 meter squared is known as a Pascal. It's a unit of pressure. It's the very same unit of pressure that was used there. It's exactly what it is. This is internal pressure, if you will, in a loaded member. We typically are going to be working with very large forces, so it's much more likely that we'll look at kilopascals and megapascals, even gigapascals, rather than just pascals themselves. But that's just a matter of us taking care of the units as we work through these. Since we are American academics, we also need to look at American units. Typically, look at them in pounds per square inch. Again, since we're talking about rather large forces, for the most part in some of these structures, we'll be looking at more likely kilopounds or kip per square inch, also known as a KSI, which is a kip per square inch. A kip is 1,000 pounds, a kilopound. We're going to have to get used to some slightly different units because these numbers typically can get rather large. All right, so we're looking here at the stress in a material, the force it's maintaining divided by the area of the material that's maintaining that force, that's resisting that force, if you will. The main loading we'll look at now for the first couple steps through this is either a tensile force or a compressive force. For several materials, their response to tensile loads is very much the same as their response to compressive loads. Steel, structural steel, is very much that kind of material where its ability to withstand stresses is about the same whether it's in tension or compression. That's not true with several other common structural materials. For example, wood. Wood is very good in compression. It's terrible in tension. It's a factor of somewhere around 8 to 13 difference. If you're building something, you typically don't want to hang it with wood structural members. If you're going to build a shelving system that hangs from the ceiling of your garage, you're going to want to have it hang from chains or cables rather than from wood straps themselves. Concrete is also that way. Very good in compression, not very good in tension. We're going to have to deal with that later in the term when we look at concrete structural members because they're very commonly used in buildings, especially a lot of modern skyscrapers. It's a very easy material to work with. It can be transported in its mixed form and then poured into the shape needed for the structures right on site. That's very useful to an architect or a structural engineer in putting things together. It adds an ability to add an aesthetic component to your structure to make it look good as well as have it behave well under these structural loads. So we've got all those kind of things that we're going to be looking at as we go through the term. Another type of simple loading, and we've looked at it some in the statics we had before, is that a structural member can have not loads that are actually directed, but are transverse to the material. Now, for the simplest statics we can do on this, those two forces have to be equal for the sum of the forces to be zero. Remember, it's also true that the moments must be zero. What we're talking about, though, when we talk about shear forces, is the situation where the distance between these two is very small, so that we're not worried about the moment that couple is causing. We're only concerned with the shear that it's causing, because if we take a look at an imaginary cut through the piece, know that causes shear forces, and that can cause a different type of damage, and it calls for a different response from the material itself, but it's still the ratio of the two, the force over the area on which it's acting, that is our concern. In this case, the force is not normal to the area, but it's parallel to the area. This is known as shear stress. And since we're assuming a uniform distribution of the force across that area, we're specifically talking about average shear stress. All right, this is the type of thing that we'll in the pins that we're using to hold these pieces together. We've never looked specifically at the pinned joints themselves. We just assumed that whatever pin was in there was strong enough to hold it. But if we look at two members that we've pinned together, we're going to do it by probably putting a rivet or a bolt or something through the piece to hold those two structural members together. That pin itself then is under these type of forces that we have here, these shear forces here. where the area of concern is right there where the maximum amount of the shear is occurring. So we're concerned with the cross-sectional area. As far as the pin itself concerned, there's no difference between a piece being in compression and a piece being in tension attached to it. The pin itself still needs to resist that internal shear no matter what the piece is, what loads it's undergoing. All right, so we're going to go to the screen here. If it comes up, good. All right, and I'll give you each a copy of this. We're going to now look at that very same structural, that object we had before, that simple triangular piece maintaining a load of 30 kilonewtons. But now we're going to look at the pieces themselves and figure out what some of the stresses are in those pieces. The places where the stress is the greatest, assuming that a piece is made out of the same material throughout, wherever the stress happens to be the greatest is going to be our place of greatest concern. So there's a lot of little structural pieces here, and we now need to look at all of them. So we'll pick one to start with. Let's look, let's see, at the member BC, the diagonal member across the top of the piece. Now, in the center of the piece, we have this cross-sectional area. The little exposed part there, for example, we have that cross-sectional area that needs to withstand the forces on there. And if I remember, that was 50 kilonewtons, was it not? And that cross-sectional area itself is, the piece has a diameter, you notice, of about 20 millimeters. So it has a cross-sectional area of, how do you figure out the area? We're assuming that's a circular piece. You can tell that from the type of shape that the person, the draftsman, put in. That indicates a circular piece. Same kind of thing I did here on the ends of my piece. That's a common engineering notation to indicate it as a circular cross-section. How do we figure out the area of a circle with a diameter of 20 millimeters? Pi times what? Pi r squared, or pi d squared over 4. And I've got that for you. 314 times 10 to the minus 6th meters squared. So we can figure out the stress in the piece at that cross-section by simply determining the ratio of the force to the area that's withstanding that. So it's 50 kilonewtons over the 314 times 10 to the minus 6th meters squared. What units? It's easy enough to divide those numbers. I'll give it to you. It's 159, and this is in tension, so we'll tend to call that a plus. You figure out what units. Let everybody think, David. Joey, you don't want to think yet? It's really 8 o'clock on the first day. 50 times 10 to the third newtons, that's a kilonewton, over, we'll call it about 3 times 10 to the minus 6th meters squared. 50 over, what, 0.3. So that would change this to 10 to the minus, the 50 over the 0.3 will give us the 159, is that right? So this will be now 3.14 times 10 to the minus 3. So we have 10 to the third over 10 to the minus 3. They cancel? Of course not, they're not the same. Have to be the same to cancel. So it's 10 to the 6th. That puts it just in the newtons per meter squared, or 10 megapascals. In engineering, it has long been the tradition to keep the exponents on the scientific notation in multiples of 3. Do you know why that's long been the tradition? Because it's certainly not necessary. We have these prefixes for just about any number. No reason we have to stick to multiples of 3. Anybody know why? The tradition has long been stick to multiples of 3 if possible. You can't possibly know. That's why you're looking at me so puzzled. When I was a baby engineer, everything we did was done on a slide rule. A slide rule can do division of two numbers very easily, but it cannot take into account where the decimal point itself goes. That had to be done, we had to do that ourselves by doing this very type of thing, writing it down. We could do the division on a slide rule, but then we had to look at the scientific notation itself and figure out what result was then, and it's just a lot easier to do that in multiples of 3 rather than get 7s and 4s and all kinds of different things thrown in there. It was just easier to keep everything as a multiple of 3 to make life a little bit easier on the slide rule. Not a concern anymore. It's not nearly often as done that we keep these in multiples of 3 because you just enter the whole number on your calculator and do the division straight away and take whatever's written down. But I can't guarantee you're not going to end up working at some place where the tradition is maintained very closely. It could well be. It also does simplify things, and it keeps the number of prefixes that we need to remember down. Kilo, mega, and giga are our main ones. We'll use micro a little bit in a step coming up here soon. Just a little bit of history for you. I guess I should ask, does everybody know what a slide rule is? Joy, you know it? Okay, in my office I had one of those 6-foot yellow ones. That's the one I used to carry around as a freshman. Those were our calculators. In fact, one very nice thing about a slide rule is they automatically maintain the right number of significant figures in an answer, because you simply cannot read a slide rule to any greater accuracy than 2 or 3 places, and that's automatically maintained through the piece. In fact, one way they used to get greater accuracy, more significant figures on a slide rule, is they simply built them bigger. I have my grandfather's slide rule. It's this long, and it's got a magnifying glass over the slider hairline so you can read it even more closely. It can be more finely divided. I imagine it was a very expensive piece. Comes in a leather embossed case with his name in gold letters on it. What?
Texas Instrument 01.
It was a big deal. And if you go on eBay, there's people that are trading in slide rules as now almost like archaeological pieces. Very few people actually still use them. All right, so there's other places then we need to now concern ourselves. For example, up here at the end C, if you look at the drawing there and see what we've got, the piece at end C actually flattened out a little bit so that it will then mate with the other piece there, and there's a hole put through it. But I'm looking at the upper end of the piece of BC, the diagonal piece that goes across here. It's actually the same thing as the end down at B. That's a concern for us because now the cross-sectional area that's maintaining the force, internal force, has changed. If we look right across there, that area still needs to withstand the 50 kilonewton load. If we look at it in cross-section, it looks something like this. There's the hole, and now there's the cross-sectional area that's trying to maintain, to withstand that 50 kilonewton loads. Because the 50 kilonewton load hasn't changed anywhere along the piece. But now the area has changed that's withstanding that load. And so that piece is now, let's see, I think this is 40 millimeters across there, is that right? And the diameter of the pin, because that's also the diameter of the hole through that piece. Make sure you know how to read these. It's that pin through there, D, that's making this hole. That's a 25 millimeter in diameter hole, which means the area maintaining that 50 kilonewtons load has changed. So let's see how it changes the stress in the material at that point. The force is still the 50 kilonewtons. Yeah, there's a little bit of friction between the wall attachment and that piece C, but we're not concerning ourselves. Remember, we're looking at these unless otherwise said that are freely pinned pieces. So the friction there is very small. So this is 40 by, what's that distance? 40 minus 25 is, yeah, so that's 17 and a half, but there's two of them on either side, so we can concern ourselves with just the full area. 40 by 15 millimeters squared, and that's what? 600 millimeters squared. Is that right? So what's the stress in that piece? That way we can compare it to the stress in this piece. Again, this is still a tensile load, so we'll call it a plus. So the stress in that piece now, who's got the calculator out? Anybody? David, you do. Did I do it right? What?
The stress in the cross section?
Yeah. This is the cross section. The 40 by 15 is right, isn't it? Isn't that the hatched area? Because remember, the whole area has been removed. So it's not there to withstand any of this 50 kilonewtons. The 50 kilonewton force is now only through those two areas. The pin is not withstanding any of this tensile force. It's just holding the two pieces together. We'll have to look at the pin separately, because the pin is in shear, but the member itself is in normal stress. David, what's that come out to be?
I've got 3.3.
Something's wrong then.
Okay.
That's not the number I had. What did I do? Something's wrong there.
I put in 50 kilonewtons as 50,000. Oh, it's in millimeters.
This isn't right at all. Because the area, we also have to take into account the thickness of it, which is 20 millimeters. Then it's times the 40 minus the 15 millimeters squared. Because I didn't take into account that thickness, which is 20. Okay, so 40 minus 15 is what, 25 times 20 is 500. That's still not right. 300, I meant. No, okay, that's right, now we're okay. Yeah, 40 minus 25, 15 is the result. Whew. It's my first day too. Is that better? Is that now the cross-hatched area that's maintaining, that's resisting that force? Okay, that's a little bit better. So it should be about 167 megapascals. Is that about right now that we got the numbers worked out? So notice that in the center of the piece we had just under 160. Now we've got somewhat over 160. As a designer, your concern is more now with the end piece withstanding that load, because it's under greater stress than is the center of the piece itself. Not by a lot. Typically when you design structural materials, you throw in a factor of safety of at least 2 anyway. But it does highlight the fact that the concern is not in the middle of the piece, but at the end where the shape of the piece has been changed and is now pinned through. All right, let's see, any questions? And what else can we look at? Let's look at the piece AB now. AB, you'll notice, is a rectangular piece. So its interior cross-section, somewhere in the center, is something like that. Imagine where this cut is. It's in compression, remember. If I remember, by 40 kilonewtons. So what now is the compressive stress in this piece through the center of the piece AB? It's got to maintain the 40 kilonewtons, but over what area? It's this cross-sectional area here, so it's the thickness divided by the depth. Looks like it's 50, and this is millimeters. How deep is the piece? Everybody agree with that, 30? You actually have to look down at this piece here. Here's AB here, and you can see then its thickness is 30 millimeters there. So the area is 600 square millimeters, 1,500. Looks a little better. So the compressive stress in that one, we'll give it a minus sign to indicate compression if we need to. Since we're not talking about what specifically this material is, we're not directly concerned with whether it's compression or tension, but we certainly will be when we specify what the material is. We have to look at their response, the material response in compression and in tension. So what do we get for a stress there? 7. One thing we're going to look at later in the term is there's a different type of failure in a piece like that's under compression where it can deflect sideways, just like a column would when it's loaded. And we're going to have to look at how it resists the tendency of it to bow out laterally and in what direction it'll do that. Then we have that, so we can look then at this other end here where part AB now comes into a U connection, and it's now the cross-sectional area. This is now at point B. It's now this cross-sectional area that needs to withstand the same 40 kilonewtons that was in the rest of the piece as a whole. I think by inspection you can see that there's more area there, so that's going to be of less concern in terms of failure than the original piece, the center of the piece. All right, any questions so far? Pretty straightforward. It's not too terribly different than what you might have put together yourselves anyway. This idea that we're concerned with the force being exerted divided by the area that's withstanding that force. It makes a lot more sense to do it that way than it does the product of the two. Next point of concern maybe, let's look at the pin at point A. Got a U-shaped connection at the wall. That's this U bracket that's mounted right on the wall. And then the structural member AB fits in there, and it's all pinned together. Now, that pin at A is now under shear stresses such that there's a 40 kilonewton force there and 220 kilonewton loads there. Just by symmetry of it, I know that it's the 220 kilonewton loads over that pin A. If we look at this little piece here, it's got a 40 kilonewton load that way from the member AB itself, and we must have shear of 20 kilonewtons across that face there. This, by the way, is called double shear for hopefully obvious reasons. There's shear at two places of equal size on the piece. Is this piece in equilibrium? Yes or no? Phil, you're nodding? Samantha, you're nodding? Yeah? David? Yeah, this piece is in equilibrium because whatever couple is caused by the 20 kilonewton is defeated by the 40 kilonewton itself. So the shear then, or the shear stress then, is what? How much shear is being withstood by how much area? Do I put in 20 kilonewtons here, or do I put in 40? What's your feeling? It depends. It depends on what area is put in. If I put in the 20, then I put in just one of these areas withstanding that 20. If I put in the full 40, I've got two areas withstanding that, but either way the ratio comes out to be the same. But it's the force being resisted divided by the area resisting it. In this case we have a 25 millimeter area, so just one of those areas is withstanding the 20 kilonewtons. If you put in the full 40, you double the area and you get the same ratio anyway. What's that come out to be? Got it, David?
Than what you have on this. That would be fine.
Maybe with a little bit of round off here or so. I don't want that. I want the shear stress. Oh yeah, 25 over 2 then squared. Good catch, thank you. 40.7 what? Is that a question mark?
I'm not sure if they use pascals and shear.
Either one. It's not strictly a pressure, but we still use the same units. Still use pascals. 40.7 without any scientific part to it, any scientific notation part to it, is megapascals.
I think so.
Depending on what material that is, you need to look at the ability of the material to withstand the shear stress. Certain materials, it's very much a concern of how they react to shear stresses. For example, if you look at a piece of wood as a pin, which is very common, if any of you, especially in the Adirondacks, we have a lot of those timber peg homes where the girders and the joists and all the structural members are held with wood pins, actually driven into the holes. If the grain of the wood runs this way, then the wood pin is very good in shear. If they cut those pins such that the wood grain ran this way, then it's terrible in shear, and that wouldn't last very long. If you even go buy a simple dowel at Home Depot or Lowe's, all of them are with the grain this way. You can't even find a piece. Nobody would do it. It just wouldn't hold, wouldn't suffice. All right, any questions? There's other places that could be of concern, and we need to look. We need to look at, if you were actually designing this, you need to look at every single one of the ends as well as the places themselves. For example, if we look at pin B, pin B is a rather interesting piece itself because it's got several loads coming in there, and they all come in different directions. For example, the 30 kilonewtons, which is straight down, is actually over 2 areas that are supported by this little bracket piece. So we actually have 1, 2, 3, 4, 5 areas on B that need to maintain some of the load. The 2 skinny outside areas where that bracket is, and then the 3 areas, I guess, that are about the same size that need to maintain where the structural pieces come in. So if we try to draw these in some direction, let's see. On the 2 outside slender pieces, now I'm not showing even the outside part of the pin that's not in contact with any area because there's no load on that. There's no load on it, there's no shear concern there on those parts of the faces. By symmetry, we assume half of the 30 kilonewton load is on each one of those. And then the part B, AB comes in, that's this U bracket at the end of that, so that's the 2 pieces, and the piece itself is in compression. What was the load in that? 40 kilonewtons, right? So there's 20 kilonewtons on each of these. And then the diagonal piece itself comes down, B, that's just the center piece now, and it's in pieces in tension, so it's pulling on the pin there. And so we have those loads, a little difficult to draw, as 3-dimensional things always are, but that's the type of thing that's happening at pin B. If we turn it on its side, see the 2 15 kilonewton loads coming down like that, the 2 20 kilonewton loads doing that, and then the 50 kilonewton load doing that. The concern with this pin, the pin in B, is which one of those faces, we have these 4 different faces where there's 4 different shears going on, which one of those faces is subject to the greatest shear stress? Because you have to design for the greatest load in order to maintain all of the loads. The area is the same for them. Let's label these faces with just some reference letters. E, F, G, and H. What's the shear at face E? Actually, I gotta draw that one, acting on that section. So if I look at just the face E, the first face where we're seeing shear, it's the face between this U bracket, the load bracket, and the end of the piece AB. What loads are on, what shear load is on that face, and is that the face of concern? That's maintaining just one of the 15 kilonewton loads. The same thing is going on at face H, just flipped around, the mirror image of it, so we don't need to look at that. And that puts an internal shear of 15 kilonewtons at the face E. That again is the load bracket pulling down on the pin. And so the shear stress at face E is 15 kilonewtons. And what's the area of pin B that's withstanding that 15 kilonewtons? Pin B is how big? Here's pin B, 25 millimeters. And so what's the shear there? 30.5? Looks good enough. Any units? Pascals. All right, so your get out of class question. What's the shear at face F or G? They'd be the same either one. What's the shear stress at face F and G? Let's see, this one's a little bit, probably easier to look at it on end because it's got the 2 loads like that. It's only half of the loads from the members because there's 2 sides maintaining this. Both F and G are resisting this, so we only put half of the loads there. What's the shear? And the area is still the same. It's the same pin. It's impossible, I guess, that we could have a pin that changes in area, but we don't in this case, just a simple cylindrical pin. Put in and then held with Clovis pins. Got it? You ready? Okay, first get out of class question. Area is no trouble, same pin, same area, but what's the shear there? Once we know what the shear is, we just put it in divide, it's real easy. What is the shear there? Is it 35? Remember, we don't add the magnitudes of vectors, we add the vectors themselves. So those 2 vectors added together have got to be resisted by a shear across the face, something like that. How big would it be? 25 kilonewtons. In fact, that's our 3, 4, 5 triangle again. And again, if you look at the 2 areas, F and G together, they're maintaining 50 kilonewtons, and you double the area, you get the same ratio anyway. And you get 50.9 megapascal.